deal in this course at least primarily with propeller-driven airplanes. Wish we could get a jet, but I did that. My first solo airplane was a jet. It's been downhill ever since. I went to Air Force pilot training when it was all jet. And my first solo airplane was a Cessna T-37, which was a fun little airplane to fly. And, you know, I still wish I could afford to own one. but the problem is that little J69 engine, fairly early jet technology, and it wolfed a lot of fuel. And so I certainly couldn't afford one. It would have to be re-engined with a more modern engine than what the T-37 had. All right, but we're dealing with propellers, so we'll talk a little bit about propeller theory. And had a good question right before lunch, and that was, take an airplane like a Cherokee Warrior, why does it only have a RPM gauge and not a manifold pressure gauge?
Fixed pitch.
It's a fixed pitch airplane, and a fixed pitch propeller can only absorb so much torque. And so you can essentially you can turn the RPM, and we'll talk about this a little later in the course about how you test a fixed pitch propeller and do the level flight performance for them. And when you do that, you can develop a power chart for the airplane at the same time you're getting its cruise speed. So we'll talk about that more later. Today we'll talk about propeller, a little bit about propeller theory, and essentially the theory on propellers and helicopter rotors is all the same, except a helicopter in hover, you can't use the efficiency thing because you'll end up getting a zero. So they come up with a term they call, in hover, they call figure of merit in helicopters. So we'll talk about some of those differences. There are three different theories that are used for propeller or rotor theory. Momentum theory, which is the simplest of the whole thing, but it's essentially momentum theory is the best you can do, and we'll talk a little more about that too. Blade element theory, which most of the current propellers were designed on, or helicopter rotors were designed using blade element theory, and we'll go into it in a little more detail. And then vortex theory, which has really only been used in recent years since we've had high-speed digital computers to be able to solve some of those equations. But most of today's propellers were designed using blade element theory. Really, for an airplane designer, the problem is really finding an existing propeller design that can be adapted to their requirements. If you pick up the phone and call Hartsell Propeller up in Pequay, Ohio, and say, designing this new airplane and I need a propeller for it, what they will generally tell you is, well, we've got, they'll rattle off all the terms for a particular propeller blade that they already have designed, and we'll sell you that one. It's not often that they're going to design you a completely new propeller, so they're probably going to, it's probably going to be select something that already exists. Only recently has there been designed with using vortex theory, like I say, since I know some of the companies now are starting to use that. But again, you have to, you can't just like a new airplane, you can't design a new propeller every time you get a new requirement. Just because of the cost of doing the design and certification work. So generally it doesn't happen that often. Well, let's talk a little bit about momentum theory. In momentum theory, essentially, it's just Newton's second law, where we have the force generated by it is equal to the mass times the acceleration or change in velocity with time. And the assumptions of this are that the propeller doesn't add any rotation to the airflow. We know that isn't exactly true, but that's one of the assumptions. There are no propeller drag losses, and the air is inviscid and incompressible. And the propeller or rotor has an infinite number of blades. It's really a disc rather than has blades. And so we can come up with an actuator disc that's here. That would represent our propeller. And we have this control volume, and way out here is infinitive, and our initial condition. As the flow comes into this thing, we have a jump in velocity across the propeller and a jump in pressure. And as we get far downstream, we we're back to the original pressure far downstream, but the velocity is downstream is twice the velocity jump across the propeller. You've probably seen this before in some other case. And a couple of things from this control volume. This area here across this propeller is twice the area far downstream, and far downstream the velocity is the initial velocity plus twice the velocity increase across the propeller. And so we can write some equations for that. The mass of air passing through that control volume per unit time looks like this, where mass is the density times that area of the propeller disc times the free stream velocity plus the velocity increase, and then we can write the thrust. We have end up being the mass times the velocity, and that's the part in the equation plus 2 times that velocity jump. And the input power to the propeller or rotor in this case is the force times velocity. And the output power is just the force times the velocity. So the efficiency then becomes the output over the input, and we can write that this way, and then it becomes the velocity over the initial velocity over the initial velocity plus the jump across the propeller. Now, the thing about this is, that's going to be the best you can get. And you say, well, why are you talking about this anyway? What benefit does it have? Well, the benefit it has is that that's the best you can do. So if you end up in a job where you're evaluating a propeller or a helicopter rotor, and some guy comes up with pie in the sky and he's doing better than this, it's a bunch of hooey. It's not true. You're not going to do better than this, okay? So it's kind of a top limit. Actually, what's going to happen is something less than that, all right? Again, it goes back to those assumptions we made. If you remember, we made these 4 assumptions. And we know that most of them aren't really true. You know, there's something less than that, so that's why it comes out that way. Okay, so let's get a little more realistic. Blade element theory considers the propeller to be a highly twisted wing, okay? And most propellers that we have today were designed using blade element theory, as were most helicopter rotors. And we said it considers it to be a highly twisted wing, and so we're going to try to combine these propeller parameters to more familiar wing parameters. The fact that this thing is rotating kind of makes it hard to make exact comparison with wing parameters, so we're come up with some new ones, and these are some of them. You know, on the fact that it is rotating, so it has a rotational velocity, and then we have the aircraft's velocity through the air. And so when we do that, if we take an element, some blade element here, we'll say this is it, some radius out on the propeller, and we look at it, we can see that here's the airplane velocity, okay, or the forward velocity that it's making. Here is the blade angle, this angle between here. This is the rotational velocity here, okay, the forward velocity. And then the blade angle is right here to here. But the angle of attack is just the difference between these two of that blade element. Well, you know, and then each blade element then is going to have a different angle of attack if we use wing theory. So that, you know, that doesn't work too well, so we come up with some other things. Gamma in this case, gamma is the reduction, or I'm sorry, this is gamma, this is a reduction, angle of attack is here, I'm sorry, I made a mistake there. But this reduction in the blade angle due to the rotation, we call gamma. Now again, you know, we also in the flight test world call climb angle, or that sort of thing. We call it gamma too. Well, we run out of Greek letters and alphabet, you know, in engineering. And so as a result, we end up using things more than once, and so you have to be careful, you know, in using these terms and talking about them, because it's very easy to confuse one for the other. So the U term here is that velocity due to rotation. Okay, so then if the blade angle is fixed for a given blade element, then the angle of attack is just the blade angle, beta, minus the gamma, or that reduction thing. So for propeller, alpha is different for each blade element, and really isn't very useful. And so better method is to evaluate the propeller at the tip, since the blade twist is fixed throughout the span of the blade, okay? So the tangent of the blade angle to tip is equal to 2 times the velocity, forward velocity, over omega, the rotational velocity, times the diameter of the propeller, or, and omega is just pi times the revolutions per second. And of course, D in this case is a propeller diameter. And a dimensionless quantity V over ND is pi times the tangent of that blade angle at the tip. And we call that the advance ratio, okay? And the advance ratio is abbreviated with a capital letter J, and it's just equal to the velocity of the aircraft through the air over revolutions per second, N, times the diameter. And so we use advance ratio to replace angle of attack in airfoil theory, in propeller theory. All right, with propeller theory, we use advance ratio and instead of angle of attack. Some cases for helicopter rotors, you'll see this being given as mu. Again, why? It's just, they're the same thing. Well, if we use this concept, we know that the resultant velocity of a given blade element is proportional to the revolutions per second times the diameter, and that the aircraft velocity is equal to the product of advance ratio and the revolutions per second times the diameter. And the rotational velocity, U, is equal to 2 pi times the radius divided by the diameter times revolutions per second times the diameter. So we can arrive at an equation for the thrust generated by the propeller using the laws of similarity. And the propeller diameter we use as the reference length in determining the Reynolds number. The thrust is the product then of d squared, diameter squared, and the dynamic pressure, which corresponds to revolutions per second times the diameter, and a thrust coefficient, C sub t, which is a function of the advance ratio J and the Reynolds number. And so for a common Reynolds number, then it's just a function of the advance ratio. So the thrust is equal to the density, air density, times revolutions per second times diameter, that term squared, times the diameter squared, times the thrust coefficient, C sub t, and that's equal to rho n squared d to the 4 times ct. Now, compare that to the lift equation. Okay, we'll replace thrust by lift from wing theory. And what we have is that essentially the C sub t is like C sub L. And the, 1/2 rho v squared is absorbed into that whole thing. So in propeller theory, we plot C sub t versus advance ratio, or thrust coefficient versus advance ratio, just like we plot lift coefficient versus angle of attack. Okay, and before we didn't consider in our simple-minded theory, we didn't consider the drag, right? Remember, that was one of the things we said that when we looked at momentum theory, we said, oh, we'll just say that this thing doesn't have any drag. Well, it does have drag. And so in blade element theory, we do consider that. And here it is. The drag is made up as a part of the moment required to drive the propeller, and that propeller torque Q is equal to, again, air density, revolutions per second squared, diameter of the propeller to the 5th power, times a torque coefficient, C sub Q, and that's dependent upon, again, our friend's advance ratio, Reynolds number, and the shape of the propeller. So, the input power then that we have to put in ends up being, again, much like the drag coefficient. Well, we have the torque coefficient here, and we're going to say, well, if we say the torque coefficient, or the power coefficient, we'll call it just 2 pi times the torque, And we can write this thing with the power coefficient, which is like drag coefficient. So the input power is the density, revolutions per second cubed, diameter of the propeller to the 5th power, and the power coefficient. And since CQ was dependent upon advance ratio and propeller shape and Reynolds number, so is C sub P. And then we can plot these things like this. The power coefficient is similar to the drag coefficient of airfoil theory, and is usually also plotted versus J. So here we have C sub T. You know, that looks like a CL alpha curve turned on its side. Okay, and our C sub T, I'm sorry, this one, and we have C sub P that looks like essentially drag coefficient plot. All versus our new angle of attack, which we call advance ratio. Now, that's just for a single propeller element. And from that, what we see is this single, fixed pitch propeller has one place where it is the most efficient. I say one place, one advance ratio, and remember J equals V velocity over ND. So if ND are the same, then it only has a efficiency at one airspeed. So this the Warrior, let's just use it for an example since that was a question I had. A Warrior, the propeller on it is only most efficient at one airspeed. Every place else in its flight regime, it's off max efficiency. Now, what we can do is we can take and we can make a plot of J, or airspeed, we'll say, and propeller efficiency for a propeller that we can change the blade angle. And so we have curve that looks like that, curve that looks like that, curve that looks like that, curve that looks like that. The propeller is operating up here. And that's the kind of thing we have on the Cherokee 6. We have a constant speed propeller where it is operating up here on the peaks of these efficiency angles. However, a fixed pitch propeller, this looks like this. There's only one advance ratio where it's the most efficient. You may have heard in some time about a cruise prop and a climb prop.
So speak of that, which one you're gonna use, but if you're gonna climb most of the time?
If you're going to climb most of the time, then yeah, you want this peak down here at your climb speed, right? If you're designing an airplane, for instance, that's going to just tow gliders up all the time, okay? An example is the Polish have an airplane called a Wilga. Some of you may have seen them Wilgas. Well, a Wilga, that's its purpose, is to tow gliders. So it would be optimized at that best climb speed because the idea in towing gliders is to get the thing up there in a hurry and then come back down and get the next guy. Well, a cruise prop would be optimized at a higher advance ratio or a higher cruise speed, since J is really a function of velocity. So you would want it optimized at the higher speed, and it would be really off optimum at climb. So with a cruise prop, you're not going to climb very well, but you'll go faster. With a climb prop, you're going to climb faster, but you're not going to cruise very fast. So, an airplane like the Warrior, it's optimized somewhere in the middle. You know, with its fixed pitch, it's optimized someplace in the middle to give you good enough climb, you know, that you're happy with the climb, and a good enough cruise that you're gonna get someplace without being. And so that's the purpose in a constant speed propeller, is that you're operating up here on the tops of all these curves throughout the speed range. It's changing blade angle to maintain that position. Okay, does that make sense?
Is there a way to
Yes.
check, is there a way to check that on the airplane? Like you read the MP, is the MP the driver? Say you're flying with an optimal angle of attack on the prop.
Yeah, usually you can generate on an airplane like the Cherokee 6, you can generate this top curve, okay, by essentially doing a level acceleration. We'll talk about level accelerations later, but essentially you can generate that curve.